Welcome everybody to week 7 in review. So this week we covered two topics. We covered observability, and we also covered the idea of a linear time observer. And as you'll see, conceptually and also in terms of the mechanics, these are very related to the concepts of reachability and also linear state feedback. Okay, so let's first start with observability. The idea here is that we've got x dot is equal to ax plus bu, and the new element here introduced in, I should say that this is all covered in chapter 7 of the book. The new element is that we no longer have access to x itself, we only have access to observations y equals c of x. So y could be something like 0, 0, 1 times x. That means that all we get to see is just x3. Another example might be that y is equal to 1/3, 1/3, 1/3 times x, and what would this correspond to? Well, just multiplying this out, we see that this is really the average of the x's. x1 plus x2 plus x3. So the question is, if you're only allowed to observe something like y, then can we design an x hat so that x hat converges to x? This is question 2 above. And also, a very related question is, can we estimate x itself? So let's answer these in reverse. Can we estimate x itself? And this will give us the definition of observability. So let's go back to a discrete time system. We've got x of k plus 1 is equal to a x of k plus b u of k. As we showed in class, for simplicity, we can just ignore u. And y of k plus 1 is equal to c x of k plus 1. Okay, so this is the output that you see. So the question is, given y of k, given the sequence, given all of y of k, say from k equals 0 to t, can we compute the sequence x of k in the same range? As we pointed out in class, this is equivalent to computing simply x of 0. So why is that? Why is knowing x of 0 the same as knowing the complete trajectory? Well, it's simple. The answer is that there's no noise, there's no stochasticity, there's nothing random in what we're discussing. So if you know x of 0, and you know the dynamics, so whenever we mean the dynamics, we really mean we know the matrices A, B, although we're ignoring B here, and C. In other words, you know that x of k plus 1 is equal to A x of k plus B u of k. Y is equal to C x of k. Well, then it's easy to compute all of x. In fact, all you just need is this. You don't even need C. Because we know that, as we've shown many times, that at any time k, x of k is equal to a to the k times x of 0 plus this summation of a to the k minus I minus 1 b u of I, from I equals 0 to k minus 1. So you see, in order to compute x of k, you need to know A, you need to know B in the input, and the critical piece that we need is x of 0. So if you know x of 0, then using the dynamics, you can basically compute everything. So now all we need to do is write down equations for x of 0. So at time 0, we know that y of 0 is equal to c x of 0. That's one equation. We know c, and we get to observe y of 0. At time 1, we have y of 1 is equal to c x of 1, which is equal to c a x of 0 when we're ignoring the u terms, etc. So down by time k, we get to see c times x of k, which is just equal to c a to the k times x of 0. So writing these all together, we see that the left-hand side is something that we know, y of 0 down to y of k, is equal to the matrix, which is called the observability matrix. And note that these are now row vectors. C is a row vector, and C times A is a row vector. And of course, all powers of C times A then is a row vector, times x of 0. So the question is, given that we know this, that's what we observe, and we know this because we know the dynamics, when can we compute x of 0? That's the main question. And the answer, of course, is we can do this when the rank of the matrix, C all the way down to C a to the k, is equal to n, where n is the dimension. So this gives us our definition. So recall that this is very, very similar to our definition of reachability. So we have our definition. A system, or sometimes we'll just say a pair A and C, is called observable if the rank of this matrix is equal to n. And note that this is now an n by n matrix. So in other words, another way to test it is by checking the determinant. So equivalently, A and C, the pair, is observable if the determinant of this same matrix is anything different from 0. So that's observability. So now let's go into the second topic of designing a linear time observer. And the idea here is the following. We've got x dot is equal to ax plus bu. Y is equal to cx. We're back in continuous time, but everything that I'm saying here applies to discrete time as well. And what we want, okay, so we do not know x of 0. Hence, we do not know x at time t. So what we'd like to do is design a linear time invariant LTI system in new variables. These are variables that you're going to simulate on your computer, or you're going to create using integrators. New variables x hat such that x hat converges to x. So this is what we would like to do. So which of the dynamics of x hat be? Well, naturally we'd like them to be very close to the dynamics of x. But if we just have exactly the same dynamics of x, well, unless we happen to know the origination point, x of 0, which we don't know, then we don't know how to start this. We don't know what the initial conditions are for x hat. And therefore, the difference between x hat and x could be very big, it could be growing. So the idea is we're going to compensate for this by adding a new term that we're going to design. So we design L. And what it's going to multiply is y minus y hat. Now why does this make sense? because y is the output that we observe, y hat is the output of our made-up system, and if those two are different, then x hat is definitely not the same as x. Okay, so this is why this is a sensible thing to do. So the question is how to design L. This is one of our questions. So let's write the error. So let's write x tilde as the difference between x and x hat. Now what are the dynamics of x tilde? X tilde dot is just x dot minus x hat dot, and plugging in what we know, this is ax plus bu minus ax hat plus bu plus ly minus y hat. Notice that the bu's cancel, and we're left with a times x minus x hat minus L, and let me write y as cx and y hat as cx hat. So minus L times c times x minus x hat. And noting that x tilde is x minus x hat, we can therefore write that x tilde dot is equal to ax tilde minus lc x tilde, or x tilde dot is equal to a minus lc times x tilde. Now, recall, x tilde is the error, and we want the error to go to 0. Right? This is what we want. So how do we do that? Well, we need to make sure that this is stable. So if the eigenvalues of a minus lc are in the open left-hand plane, then what's the error going to look like? X tilde of t is equal to e to the a minus lc times t times x tilde of 0. What's x tilde of 0? This is our initial error. This could be big because we had no idea where the original system was. But the point is it doesn't matter, because if the eigenvalues of a minus lc are on the left-half plane, this decays to 0 exponentially fast, which means that the error decays to 0 exponentially fast, which is exactly the same thing as saying that x hat converges to x exponentially fast, which is what we want. Okay, so our goal now becomes, we've reduced this to something very familiar. Choose L so that A minus LC has eigenvalues in the left-half plane, or another way to say it is choose L so that A minus LC is stable. Now, how do we do this? Exactly like we did it for reachable canonical form. So let's define. A and C are in observer canonical form if A has the special form minus an minus 1 minus an minus 2 all the way down to minus a0, and then 1's just above the diagonal. Okay, so this is the diagonal, and the 1's are just above it. And C has to have the special form 1 and then 0s. So note how very, very similar this looks to reachable canonical form. In fact, these are just transposes of reachable canonical form. Okay, so, and why is this great for us? Well, so let's suppose suppose the pair A and C is in observer canonical form, and we want to design L. So L is going to be an n by 1 vector, L1 to Ln. What's LC? LC, if C is a part of a pair that's in observer canonical form, is going to be the matrix, the n by n matrix, L1 to Ln, with zeros everywhere else. And therefore, A minus LC is going to look like minus an minus 1 minus L1, all the way down to minus A0 minus Ln, with zeros, oops, not with zeros, with ones just above the diagonal. In other words, A minus LC is also going to have this special form. And the reason that this is so great is exactly the reason why we liked it in reachable canonical form, because the characteristic polynomial of anything in this form, let me just do it for A, is just equal to lambda to the n, now with all the signs reversed, plus an minus 1 lambda to the n minus 1, all the way down to plus a0. So in other words, the characteristic polynomial of lambda I minus a minus LC is just going to be lambda n plus an minus 1 plus L1, lambda to the n minus 1, all the way down to a0 plus Ln. Note that, again, exactly, I'm like a broken record here, exactly like in reachable canonical form, we control all the coefficients of this polynomial. So all we need to do is, in order to choose L properly, is choose a polynomial that we like, that we know has coefficients on the left-half plane, multiply it out, and equate coefficients. So choose roots that we like in the open left-half plane. I always like choosing them all at -1 because then you can use Pascal's triangle. Find the resulting characteristic polynomial. So if you chose roots, say, Ri, then the resulting characteristic polynomial would be the product of lambda minus Ri. And then equate coefficients to solve for the lambda I. Okay, exactly like reachable canonical form. Now the final thing we have to do is, what if a system is not in observer canonical form? Well, we showed this fact in class, that if A and C, if this pair is observable, then there exists an invertible matrix T such that if we do the change of coordinates z equals tx, and we look at the dynamics in z, which means z dot will be ta t inverse z. We've done this many times before, so I'm going over it quickly. Plus tb times u, and y is equal to c, but not c times x, but c times x, which is equal to t inverse z. Then the pair a hat c hat, which is given above, so this is c hat, that's a hat, is in observer canonical form. So basically what we do is we compute T, put in observer canonical form, find L hat, and then write L in terms of L hat and T. And note that actually we really don't need T until this step. Okay, so I won't go through these details because there's some homework problems that give you practice with exactly this. So the final topic that I want to discuss is an important one. It's the separation of control and observation. So what are the two parts? Putting chapter 6 and chapter 7 together. So putting, oops, I can't make the chapter symbol. Putting chapter 6 and chapter 7 together. So in chapter 6, we saw, let's again just summarizing a very small part of Chapter 6. How we can choose K so that the feedback U minus Kx stabilizes a system. And in Chapter 7, we said, well, suppose we no longer have access to X. We can make X hat so that X hat converges to X. And so X hat is, again, the solution to the differential equation AX hat plus BU plus L times Y minus Y hat. And we showed in class how you can make the block diagram for what that would produce X hat. So the idea of putting them together is, okay, we don't have access to X anymore, so no access to X means we can no longer have U equals minus Kx because we don't have X. Well, what's a natural idea? The next best thing is to have U equals minus Kx hat. So, the question is, if U equals minus Kx stabilizes the system, and if X hat dot is equal to AX hat plus BU plus L Y minus Y hat is such that X hat converges to X, in other words, X tilde dot is equal to A minus LC X tilde is stable. So if these two things are true, then the question is, finally, does the feedback law U is equal to minus Kx hat stabilize? So we answered that in class, but let's answer it again. So let's write the dynamics. So we've got, in this case, X dot is equal to AX plus BU. U is equal to minus Kx hat. Plugging that in, we have X dot is equal to AX minus BKX hat. And see, we're a little stuck here because we don't know how to proceed. So the one way to proceed is to just augment the system. So let's write together the differential equation for X dot and X tilde. Now, note that X tilde is equal to X minus X hat, and therefore X hat is equal to X minus X tilde. So plugging this in, plugging this expression to here, we find that we have X dot is equal to AX minus BK X minus X tilde, which is the same as writing A minus BK times X plus BK X tilde. Meanwhile, the dynamics for X tilde are, just like we had before, A minus LC times X tilde. So let's write now the dynamics for both together, X dot and X tilde dot. And you can see that this is going to be a big matrix, 2n by 2n, A minus LC in the top corner, BK, 0, A minus BK up here, and A minus LC. And is this stable? Is this big matrix stable? And the answer, happily, is yes, because the eigenvalues of the big matrix are the union of the block diagonals of A minus BK and A minus LC. And our two ifs above basically said that the eigenvalues of A minus BK are in the open left half plane. The eigenvalues of A minus LC are in the open left half plane, therefore the whole matrix is stable. And note that this is what's called the separation of observation and control, because how you design K and how you design L have no impact on each other. It's not that you can design some Ks that work with some Ls. You need to design a good K, and that's independently of what the guy who's designing L is doing. And you need to design a good L. Okay, so that's the separation. And we'll stop this lecture right here.